next 2 days, we are going to be transitioning away from being so dependent upon our pictures. We've got to get to the point that we can upscale this without it taking forever and ever to get something done. We can pretty easily draw a single batch, a double batch. A triple batch starts to be a little bit annoying. But if we want to get upscaled onto a scale that we can actually do in lab, we need not millions of batches, not billions, not even trillions of batches. A trillion batches wouldn't be enough yet that we could work on it in lab. So drawing the pictures is actually going to be unrealistic in terms of representing an actual chemical reaction. Our goal in the next 2 days is to replace this picture with a table that just tells you how many particles would be in the picture if you drew the picture. Today and our next class day, we're going to draw both simultaneously, and then we're going to phase out this piece to do it just in terms of a table for much, much larger numbers. But for the next 2 days, to make the connection between the two, we're going to keep putting the table and the picture side by side. So we're going to introduce the tables, show you how to use them, and then give you some time to practice with this. This first picture is our older Bunsen burners, the ones that we used to hook up to the wall that have the methane that come in. Now I've got this one drawn as the reactants on the bottom, the products on the top. For a moment, I'm going to cover up the products part of this. Here are the steps for creating a BCA table from a picture. Step 1, fill in the before row. Filling in the before row is a counting task. So before the reaction starts, I have 1, 2 methanes. And I have 1, 2, 3, 4, 5, 6 O2s. If you get confused about what has to go in the before row, think about what a 5-year-old would say if you asked them. Okay? They would just touch every one and count them. That's all that goes in there, is the how many do you have before you start. Before the reaction starts, I haven't got any of the products. Step 2, start batching things up. In terms of making the batches, you're just going to follow the recipe. The recipe says take 1 methane and 2 oxygens and use that to spit out 1 CO2 and 2 H2Os. Okay, so now we've got to be able to see the products. Take 1 methane and 2 O2s, and that makes 1 carbon dioxide and 2 water molecules. All right. So just follow the recipe. And then do it again. Take 1 methane and 2 O2s, and that spits out 1 carbon dioxide and 2 water molecules. And then do it again. Take 1 methane. Oh wait, I can't, because I don't have 1 methane. All the CH4, or the methane, is used up. I am done making batches. Okay, so I stop doing that. Then I fill in the change row. The change row is how much you spent and how much you got. Everything that you lassoed up in the reactants part is what you spent. 1, 2. I spent, okay, negative, just like when you're using your checkbook. I spent 2 of the methanes. I also spent 1, 2, 3, 4 oxygens. So I spent 4 oxygens. And then you look at what's circled in the products area, and that's what you gained. I gained 1, 2, carbon dioxides. So that's positive 2. And I gained 1, 2, 3, 4. So I gained, that's positive 4 H2Os. The third row in a BCA table is the row for after the reaction. What you had before plus the change tells you where you are after. I had 2, I spent 2, that means I have none left. I have 6, I spent 4, that means I have 2 left. I had none and I gained 2, so now I have 2. I had none and I gained 4, so now I have 4. If your table has been made properly, the last row here will tell you what is in the picture of your products. So the picture of my products has no CH4. True. The picture of my products has 2 O2s, here and here. True. The picture of my products has 2 CO2s, one here, one here. And the picture of my products has 4 H2Os, 1, 2, 3, 4. I've been successful because my after row matches my picture. These oxygens up here that I've drawn in the after are the same oxygens as I had before the reaction started. I know this one's drawn a little bit strangely because it's kind of an up and down rather than a left and right. Think of this one as being, here's the before, here's the after. And then this is just kind of the line in between there. So these 2 oxygens didn't get used up, so they're still around when the whole process is over. Let's talk just a minute about leftovers. People do some screwy things with leftovers. But let's imagine for a moment that I have 12 eggs in my refrigerator. And I go home and I decide to make cookies. So I take 2 eggs out of the container, and now there's 10 eggs left in the container. What happens to the 10 eggs I did not use? I put them back in the refrigerator. Do they poof gone because I didn't use them when I made the cookies? No. And it's silly when I say it that way. But some of you will make the leftover chemicals poof gone. But then just think about the eggs. Okay? Let me give you a chemical example of things not being poof gone. Let's say we actually ran a Bunsen burner in this room. We've done this, and we're all here to talk about it. When the Bunsen burner is done doing the chemical reaction, does all the air in the room that the Bunsen burner didn't use just become poof gone? Thank goodness. You wouldn't want all the unused oxygen to simply disappear. And the fact that we can talk about having used the Bunsen burner means that all the oxygen that the Bunsen burner didn't use does not just poof gone. It was still here with us. We were able to keep on breathing. So the things that don't get used don't poof out of existence. They're just still around in the end as part of the leftover system. Okay, try the next one and we'll do a check-in after that one, and then I'll turn you loose. So I'm going to work the next one, you work the next one, and then we'll compare. So here I did my batches in multicolors because things started to kind of run together here, so I tried to do multicolored batches. According to my recipe, it's a 1 to 1 to 1 ratio. So if I take 1 copper carbonate, that reacts to form 1 copper oxide and 1 carbon dioxide. So there's the purple batch, here's the blue batch, here's the pink batch, here's the green batch. So I batch it all up. Then I look at what I spent and what I gained. I spent 1, 2, 3, 4 of copper 2 carbonates. I gained 1, 2, 3, 4 of the carbon dioxides and 1, 2, 3, 4 of the copper 2 oxides. If I had 4 and spent 4, I'm down to 0. If I had none and gained 4, I'm up to 4. I had none, I gained 4, I'm up to 4. And the after row should represent the picture after the reaction. I have 0 CuCO3s, 1, 2, 3, 4 CO2s, 1, 2, 3, 4 CuOs. My after row matches my picture. I've been successful. I do not want you to try to shortcut the process at this point by not doing the batches. Okay, so I want you to circle the batches as you do this. You have 4 more to practice with, and then you're going to get out your Chromebooks and you're going to go do a simulation. This is the link to the simulation, but it's also on Canvas. Much easier to open Canvas and just hit the link from there. You're going to pick the game, go to level 3, and the most important part of this is that you do all of these steps for the 5 questions that it's asking in the game. The goal of the game is not just the prediction part. The goal of the game is to solidify your connection between a BCA table and a picture. So I want you to take the time to do all those things for each piece of the game. Because remember, the function is not the winning of the game. The function is making a very strong connection between a picture and a BCA table. Okay, you've got the rest of the time. Get to work.